So if we were asked to solve an equation with an unknown in the base, then that could be something like, when is x squared equal to 25? And so in this particular case, we know that we can go, well, x would be equal to plus or minus the square root of 25. So x in this case would be plus or minus 5. But what do we do if we have an unknown in the index? So what I mean by that is we could be faced with a question that asks us to work out, okay, well, when is 3 to the power of x equal to 3 squared? Well, because in this particular case, I have the same base, i.e. my base in both instances here is a 3, I can just compare my indices. So because I have the same base, I just look across at my indices and I see, okay, well, this will happen if x is equal to 2. And that kind of makes sense, because if we put a 2 in for x here, on the left-hand side, we would get 3 squared, and on the right-hand side, we still have our 3 squared. So 3 squared is equal to 3 squared, and that makes sense. The problem is these can get a little bit trickier, okay? So what if we were asked to solve one like, okay, well, when is 4 to the power of x minus 1 equal to 4 to the power of 5? So once again, we're lucky that we have the same base in this case. So I can just compare my indices. So these two sides will be equal to each other if x minus 1 is equal to 5. Okay, so if we can have an x minus 1 here, instead of writing x minus 1, if I could write 5, then they would be identical, exactly the same. So we need to solve when x minus 1 is equal to 5. So of course, in this case, if x is 6. And we can check that by putting that straight back into the left-hand side of this equation. So we get 4 to the power of, well, 6 minus 1 is 5. And we know that that is equal to the right-hand side, 4 to the power of 5, because they are now identical. What do we do, though, if we don't get given the same base? So, for example, what if we were asked to find when 5 to the power of x is equal to 25? Well, by inspection, we could look at this and go, okay, well, we know that 5 squared is 25, so x is equal to 2. Okay. Now, if we wanted to do this sort of a little bit more algebraically, because these techniques will be important when we take a look at some more complicated examples, I can rewrite 25 as 5 squared. And I want to do that because now if I compare my left-hand side and my right-hand side, I have my identical bases. And if I have my identical bases, we've seen that we can just look straight across the top and kind of play spot the difference with the indices and solve some form of equation. So in this case, we see that x is equal to 2 by comparing those indices. If we do another one, so we might get given when is 2 to the power of x equal to 64 squared? Okay, so this is getting a little bit harder now. We need to, the problem that we've got is that these two bases are not the same. Okay, so 2 is most definitely not the same as 64. But I can rewrite 64 with a base of 2. Okay, so 64, if you take some time to think about it, is 2 to the power of 6. Okay, so instead of a 64, I'm now going to write 2 to the power of 6 all squared, and I've still got my 2 to the power of x over this left-hand side. And if I use my indice rule that I can just multiply this 6 and this 2 together, I now need to solve when 2 to the power of x is 2 to the power of 12. So I've taken a problem which looked a little bit tougher, and I've rewritten both sides with an identical base now of 2, and I can now compare my indices. So I see here that x has to be equal to 12. We'll do another. Let's say that we're asked to find when 3 to the power of 2x is equal to a 9th. Okay, so again, the problem being that I do not have a common base amongst both sides of my equation. So how can I rewrite a 9th? Well, let's focus down at this 9. I could rewrite 9 in terms of 3 as 3 squared. So I can rewrite this equation now as 1 over 3 squared. And well, what do I know about 1 over 3 squared? Well, I can write that using my indice rule as 3 to the minus 2. So now, if we look across at our equation, I have my left-hand side with a base of 3 and my right-hand side with a base of 3. And if I compare my indices, they must be equal to each other. So 2x has to be negative 2, and so x is minus 1 in this particular case. If we take on a slightly more challenging one now, so we need to solve when 2 to the power of x squared is equal to 1 over 8 to the power of 2/3, that's a 3, I'll redraw that 3, 2/3 minus x. Well, again, the problem being that I do not have a common base on both sides. I have a base of 2 here, and I don't have a whole lot going on here, but I've kind of got this 8, right? Now, what can I do about that 8 to write it in terms of a 2? I can write it as 2 cubed. So I can have my 1 over 2 cubed to the power of 2/3 minus x. Okay, and if I expanded those brackets out, so if I multiply this 3 out to each term, I would end up with 2 to the power of 2 minus 3x. Okay, and I can rewrite that using my indices law as 2 to the power of negative 2 plus 3x. So I take the negative of this and I bring it up to my numerator. So that's just using my law of 1 over x can be written as x to the negative 1. Okay, and this has to be equal to 2 squared. So now I can compare my indexes. Okay, I need x squared to be equal to negative 2 plus 3x. So now I'm solving a quadratic. So I'm looking for when x squared take 3x plus 2 is equal to 0. So I can factorize this to be negative 2 and negative 1. And so x can either be 2 or x can be 1 by the null factor theorem. So that one there was considerably tougher, okay? But once again, the process of what we're doing doesn't change. We're looking to express both sides with a common base. So in this case, our common base was 2. I'm going to do one more before we finish this video. So let's look at when 7 to the power of 3 plus x divided by 7 times the square root of 7 is equal to 1 over 49. So seeing 7s and a 7 down the bottom and a square root of 7, which we see here, and a 49, the base which is kind of calling out to me in this case is a 7. So let's keep my 7 to the power of 3 plus x because I've already got my base of 7 there. What's happening down here? Well, 7 times the square root of 7, I can write that as 7 times 7 to the power of a half. So the square root of 7 can be written as 7 to the power of a half. And well, if I add my indices together, 1.5, I just get 1.5. So I'm dividing here by 7 to the power of 1.5. And I can rewrite 1 over 49 as 1 over 7 squared, which can also be written as 7 to the negative 2 to get that common base of 7. Now, if I use my division rule of my indices, so I would need to subtract here. So I'm going to do 7 to the power of 3 plus x minus 1.5. And that needs to be equal to 7 to the negative 2. So all I've done here is I've just kind of, as we do with indices, if it was x squared divided by x to the power of 3, then you would do x to the power of 2 minus 3, which would be x to the minus 1. Okay, so just using that subtractive law. So I'm looking for when 7 to the power of an x plus 1.5 is equal to 7 to the minus 2. So just simplifying this bit here down a little bit. So comparing my indices, I need x plus 1.5 to be equal to negative 2. So x needs to be negative 3.5 in this case for this equation to hold true. So hopefully that's made a little bit of sense. You might want to watch those examples once or twice to make sure you really got the hang of it. Remember, starting off nice and simple at the start, we're just looking for, if we had a nice situation like this, we would have common bases and we need for those indices to be the same. So we can just look straight across, place spot the difference in an equation sense and solve for when x is 2, which is when x is equal to 2. The only reason they get a little bit harder, maybe like this one here, is because we don't have that common base. They're not both written with a base of 2. So we have to artificially kind of create that common base ourselves. So rewriting an 8 as 2 cubed, or rewriting a 49 as 7 squared.